This conference will now be recorded.
Hello everyone. Today also we will continue with chemical properties of alkynes. Now under chemical properties of alkynes, the first type is addition, and under addition we are just continuing, and 4 methods under addition we have covered, and we are now have the 5th one, which is addition of water. Now once we finish this, then the next type of reactions, there will be isomerization, polymerization, oxidation, etc. That is also under chemical properties of alkynes. So we'll start with addition of water. So when it is addition of water, you can also call it hydration. Here net addition of water is occurring, but when it will be added, it is not that water single water molecule will be added in a single step. It is not like that, but it is, if you consider the overall reaction, then it is obviously the net addition of water. So here what reagent we use, basically it is not just water we are using, we also have to use some other reagent which contains mercuric sulfate. The formula is HgSO4, sulfate salt of Ag2 plus ion, and also there will be the use of sulfuric acid. So when we will treat alkyne with water plus HgSO4 plus H2SO4, so all these together will be used as reagent, then we will get first enol intermediate. So here if I write in general way, suppose we have taken RC triple bond CH. So here one side of the CC triple bond we have R group, another side we have hydrogen. If I am treating it with water, HgSO4 and also H2SO4, these 3 reagents together. So first there will be formation of enol. Now enol means what? Enol means when there will be CC double bond and OH group is attached to it. Enol means which is combination of in and all. In and all. In means what? CC double bond, and all means what? OH group. So these two together we have the term enol. So enol is the intermediate which is first form. But this is not the ultimate product, because we know there is ketoenol tautomerism possible. So ultimately there will be rearrangement and it will be converted to the more stable carbonyl compound. And that carbonyl compound may be aldehyde, it may be ketone, and that depends on what type of, whether there is R group present. That is, I'm talking about these two substituents, it is present or not. Depending on that, there will be formation of either aldehyde or ketone as the final product. So this is the enol, which is the intermediate here. So here how the tautomerization will occur. Tautomerization means the conversion from the enol form to the keto form. So this OH bond, if it is broken, there will be formation of OC double bond here, and negative charge will be over carbon. So ultimately this hydrogen will move to this position. And what we will get RC double bond O, CH2, already CH2 is there, one more hydrogen will also be now added. So that is why we are getting this molecule. Now what this molecule is, this is RCO CH3, right? So we are getting ketone here. But suppose this R group, if it is H, then what you will get? You will get HCOCH3. So it varies. It may vary. It may be aldehyde. It may be ketone. So in this case, we are getting RCOCH3. So let me erase it and write it as RCOCH3, which is basically ketone. Fine. Now some more examples also we can get if we take some other types of substituents. If both side there is presence of R group, now what will happen? RCO CH2 R. So see here, first there will be formation of enol, and enol like this, C H OH C R. So this is CC double bond, this is enol. Now this OH bond will be broken, there will be formation of C double bond O, and you will get hydrogen here. So in this way we are getting this molecule CH. Okay, there will be one H. Now another possibility is if we take two different types of R groups. Now what will happen? So one side we have R group, another side we have R prime, right? Now whenever we have this type of two different substituents, there is a possibility of formation of two different types of enol, because now you have both sides there is different R group. It is not like the previous one where you have the same R group. Now it is different R group. So that is why two types of enol formation possible. Now directly if I write, okay, let me write the enol first. So if it is the enol CHR prime, or it may be RCH double bond COH R prime. So the OH group can be added to the left hand side carbon or the right hand side carbon. So here we have addition of OH and H already happening, and depending on whether this enol is formed, suppose this is enol 1 and this is enol 2, two possibilities are there. So from this, after ketoenol tautomerization, we will get RCOCH2 R prime, and if it is the second enol, now we will get RCH2 double bond R prime. So when it is terminal alkyne means I am talking about this type. When it is terminal alkyne, the addition of water follows the Markovnikov rule and the product is a methyl ketone. So see, when you are first making this intermediate, right? Here OH group is added to this carbon. This carbon OH group is added and this carbon H is added, and that is why you are getting this type of enol. So this is the OH group which is added. Suppose this is the H which is added, and OH is added to that carbon which is containing lesser number of hydrogen, because the even if you consider the carbocation, it will be more stable at this position. So that is it is according to Markovnikov rule. But enol is not the end product. There will be ketoenol tautomerization, so we will get ketone. If it is symmetrical internal alkyne is this one, right? Then you will get a single ketone product, because there is only one type of enol formation possible. But if it is hydration of asymmetrical alkynes is this one, then there will be formation of two different types of ketone, because there is a chance of formation of two different types of enol. In the first case, OH group is added to carbon number, suppose it is 1 carbon, this is 2 carbon, and here it is added at carbon number 2. So three different conditions we have seen here. First of all, if it is terminal alkyne, then if it is symmetrical internal alkyne and asymmetrical alkyne. Another one is also you can consider, which is the first member, that is the simplest alkyne, which is acetylene, HC111CH. So in that case you will get aldehyde, because in that case this R group will be simply H, right? So with this reaction, our hydration, that is hydration, the addition type category of reactions under the chemical properties of alkynes, that part is will be complete. Next reactions are basically because of the acidic nature of alkynes. Now acidic nature of alkynes, this is exclusively, that is very unique for alkynes, because only for alkynes the question of acidic character of this terminal hydrogen arises. It is not possible for alkene or alkane. So alkynes show acidic nature only if it contains terminal hydrogen. So only if you have this terminal hydrogen, then only this question arises. Otherwise, this question does not arise, right? So here you can see we have taken one alkane. So this is the alkane. Which alkane it is? It is basically 1, 2, 3, 4. It is butane, right? So in butane, just one hydrogen, that is this terminal three, any of these three hydrogen on this side or this side if you consider. So it is in red color. So for this hydrogen, the pK value is 50. That means when you are breaking any of these 6 carbon hydrogen, because all these 6 carbon hydrogen bonds are equivalent, any of this if you are breaking, you are getting a negative charge at this carbon or at this carbon, depending on, sorry, not this one, it is the terminal carbon. So any of this carbon, there is formation of negative charge. Now here negative charge will not be stable because this carbon is already sp3 hybridized. So look at the pK value. pK value is very high, and we know pK and acidity, these two are inversely related. Now alkene, and let me tell you what is that is pK. It is basically negative logarithm of Ka value of the corresponding acid, for which we are trying to find the pK. Sorry, for which we are trying to find the Ka value, which is the acid dissociation constant. So here our acid is butane, which is actually not acid at all, but we are just comparing the pK value. So that is why we are saying it. Next, if you consider alkene, so here we have taken propene, though it is one carbon less, but that is not the important matter. The important matter is the carbon over which the negative charge is generated. What is the hybridization of that? So when there is removal of this hydrogen, there will be negative charge generation over this carbon, right? And for alkyne, here we have taken propine. There will be negative charge generation over this carbon when you are breaking this hydrogen, carbon-hydrogen bond. pK value 42, pK value 25. So when you are moving from alkane to alkene, then you are moving from alkene to alkyne. Gradually, the pK value is decreasing. It proves that for this particular hydrogen, the acidity, that is the acidic character, that is also increasing. So here percentage S character of the sp hybridized orbital is 50% because it is one s orbital and one p orbital. One s and one p. So it is 50%, 50%. Next, if you consider sp2, it is one s, one p, another p. That means out of 100%, if you divide it by 3, it will be per orbital, because now all these three are mixed. You have 3 sp2. And the percentage will be 33%. Similarly, when it is sp3, which is a combination of 1s and 3p orbital per sp3, that is after the hybridization, you have total 4 sp3, and s character is divided among all these sp3, and it is now 25%. So 1s and 3p, so it is 1/4, right? 25%. So more is the S character, more will be the stability of the negative charge. So that is why when we are comparing this negative charge, in this case it will be formed here. When we are comparing this negative charge, it will be more stable in case of alkyne. And that is the reason why the acidity of this hydrogen is so high. Because once you dissociate, the corresponding conjugate base is very stable. All these are conjugate base, isn't it? In general, if I write any acid, suppose I am writing acid HA, you are dissociating this HA bond, you are getting H plus ion, and you are getting A minus anion, which is basically the conjugate base. So more is the stability of conjugate base, more will be the dissociation of HA, and that means the acidity is also very high because now the number of H plus ions are very high. Deprotonation of terminal acetylene gives an acetylide ion. Look at this term. This term we will be using from now on. RC triple bond C, and there will be a negative charge after removal of this H, and this is called acetylide ion. So this ion generation, it happens easily compared to alkenes and alkynes. Negative charge generation over CC double bond or single bond, it is difficult. Now, because of this acidic character, now we will study some reactions. All these reactions will be based on this particular acidic character. So basically what we will do, we will generate some negative charge by using different types of reagent. Under this acidic character based reactions, the first reaction we have formation of alkali metal acetylide. That means what? We will use some reagent which will contain alkali metal. Ethane, that is the simplest member, the first member, or acetylene, and other terminal alkyne. So ethylene and acetylene, we know this is terminal, both sides there is CH bond. And other terminal alkynes, where you have at least one triple bond CH. If you treat with strong bases such as sodium metal, so directly we are using sodium metal. Look at the temperature for 75 Kelvin. Or you can use sodamide, NaNH2, in liquid ammonia at 196. So when it is NaNH2, temperature is less, because when you are using liquid ammonia solvent, temperature cannot be very high. It is even less than 0 degree, right? To form sodium acetylide, and there is also evolution of hydrogen gas. So here the reactions you can write HC triple bond CH. I have written two of these, and 2Na. So any of this H you can remove. There will be Na and hydrogen gas formation. So as we have taken 2 moles of this, so one H from one acetylene, another H from another acetylene, together these two hydrogen atom, it will form hydrogen gas, right? Now this molecule, you can take, you can treat it again with sodium. Now both side there is formation of, that is a negative charge, you can also write here. This will be the positive part. And as we have 2 moles of it, again there will be hydrogen gas generation. Fine. So here it is mentioned as the evolution of hydrogen gas. We can also take NaNH2. Let's take another example. In this time we will take which alkyne? We have taken propane. Now if I am treating it instead of sodium metal, you can also use sodium amide in liquid ammonia. Now in this case, CH3, C triple bond, C negative. So NH2 part is basically the anion which will capture this hydrogen. This bond will be broken. So NH2 minus is combining with this hydrogen. So the byproduct you will get is now ammonia. Right? So it is basically hydrogen gas when you have taken sodium metal, when you have taken sodamide or sodium amide, that is NaNH2, then ammonia will be the byproduct. A metal acetylide is an alkyne that has had a proton removed from the terminal end by a metal. So acetylide ion is, we know it is CRC or HC triple bond C negative. But you can call metal acetylide when you have the counter ion as metal. The ion is acetylide, and when there is the counterpart metal cation, you can call it metal acetylide. Now this sodium acetylide, it can be decomposed in presence of water and it can generate acetylene again. So suppose I am taking this, just take this one, HC triple bond C Na. If you are treating it with water, what will happen? Now this C negative, it will capture proton from water because this is basic in nature. Now after capturing, there will be again formation of the original product. And as it has taken H from water, OH part of water is there, which will combine with Na and it will form NaOH, right? So in this way, we can decompose also in this type of terminal C negative charge. Now, what is the utility of this type of reaction? Suppose you want to attach this type of part or this part to some other molecule, then this can act as a very good nucleophile. So this can act as good nucleophile, isn't it? So that is the utility of generation of this type of acetylide ion. This can combine with some other compound. And sometimes it may be also required that the salt we do not need and we should want to get back the original alkyne, then this hydrolysis is a good reaction for conversion to the original CC triple bond or alkyne. This is the first reaction, formation of alkali metal acetylide, because here the counter ion is alkali metal. The second possibility is formation of heavy metal acetylide. Now we will use again metal, but it is not alkali metal, it is some heavy metal. So which heavy metal normally used? Silver plus and copper plus, Cu plus. It is not cupric, not Cu2 plus, it is Cu single positive charge. acetylene or terminal alkyne. Terminal alkyne means this type of general formula I can write. And acetylene is AC111CH, which is always having this terminal CH bond. Can also form salt, just like the sodium acetylide we have already seen in the previous slide. But now it is heavy metal cation. Now this cation we will use, no, obviously not directly, we cannot use any cation. We will use the source of this cation. So for Ag plus it is AgNO3, and for Cu plus it is cuprous chloride, that is CuCl, or sometimes it is also written as Cu2Cl2. So acetylene or terminal alkyne in presence of ammoniacal AgNO3 solution. Now this is nothing but Tollens reagent. Tollens reagent we read in aldehyde or carbonyl compounds. But here also you can see the use of ammoniacal AgNO3 solution, or it may be ammoniacal cuprous chloride. Now when it is you have taken AgNO3, there is white precipitate formation, because the silver acetylide, which is just like the sodium acetylide, only difference is instead of sodium ion as the counter ion, now you will have the Ag plus, and as it is a heavy metal, there will be precipitation, and there is a specific color. So there is a color of white precipitate if you are using AgNO3, and if you are using Cu2Cl2, there is a red precipitate of copper acetylide. Now this is, from this color, it is a common sense we can say that this reaction can be used as to determine whether you have terminal alkyne or not. Suppose you have alkyne, you want to know whether it is terminal alkyne or internal alkyne. Internal alkyne means where you do not have any terminal CH bond. Then you can do this test, because only if you have this type of terminal carbon hydrogen bond, then only this precipitation is possible. So this is a proof, evidence. Now this AgNO3 Cu2Cl2, it is used in combination with NH4OH because it is already mentioned ammoniacal. And sometimes the reagent, suppose you have been given a question where the reagent is mentioned as AgNO3 plus NH4OH or Cu2Cl2 plus NH4OH, but instead of saying that, it can also be written like this, because these two together it forms compound like this or this. So in that case, that also means that there will be generation of heavy metal acetylides. So in general, I will start with this type of molecule, which is a terminal. And when you are treating it with AgNO3 and NH4OH, that is ammoniacal AgNO3. So this is the reagent combination, but instead of writing this, even directly this is treated, then also it means the same thing. So there is formation of heavy metal acetylide. So this is red color, and there is precipitation. Precipitation sign is given. And the fate of this nitrate ion and NH4 plus is that it will form NH4NO3. And the OH from NH4OH and this H together it can make water. So this is the reaction for with AgNO3. You can also write it, it is the same molecule. You can also write it with Cu2Cl2. Here also NH4OH. Now it is CCU. And this, sorry, this is not red. This one is red. This is white. And again, there is formation of, this time it will be NH4Cl, because now you are having a chloride ion, Cu2Cl2, not nitrate ion, and water as usual. So these are the byproducts, but actual product is red precipitate of this copper acetylide or white precipitate of silver acetylide, right? So this is second reaction. Now the third reaction for the acidic nature is formation of alkynyl Grignard reagent. Acetylene and other terminal alkynes, they can react with RMGX. Now RMGX, if you break it, it is basically negative charge over R, and MGX, it will contain the positive part, because R is nothing but some carbon. Just simply take CH3MgX. Now compared to Mg, carbon is more electronegative. So when you are breaking the bond, it will be negative charge over R. Though we do not write this separately, this positive part and negative part, But here, for the sake of understanding, I have written it in this way. Better you write negative partial charge, negative positive partial charge. It is better. So these are minus. Now it will act as base. Now as it is a base, and we know that these hydrogens are acidic in nature, so this base, now it will capture this H. And as a result, there is formation of RH. And RH means what? It is alkane. So there is formation of alkane. So it is also a very good method if you want to make alkane. Though that is a byproduct, because now we are focusing on how to make alkynyl Greek reagent. So you are thinking this is the main product, but suppose you can also treat it if you want to make it. This can also be a method for formation of alkane. So this active hydrogen, whether it is AC111CH or RC111CH, R prime, because this group is R. So now you are getting a new Grignard reagent. So you have started with the old Grignard reagent, which is RMGX, but now you are getting this Grignard reagent where the R part is AC triple bond C negative and MGX. This is the again positive part. Now this is also as if from one Grignard reagent you have generated another type of Grignard reagent. That is the reaction. But this is also because of this acidic character of terminal hydrogen. Otherwise, these reactions are not possible, right? So if it is CH3MgX, then RH will be methane. If it is CH3CH2MgX, it will be CH3CH2 another H, that means CH3CH3, which is nothing but C2H6. So it depends, but alkane formation is possible. And this is alkynyl Grignard reagent because you have some alkyl group. So this is the third reaction, and this is done. That is a total 3 reactions we have discussed under the acidic nature of these terminal alkynes. Now the third type is oxidation reaction, oxidation of alkynes. So we have seen in case of alkenes some oxidation reactions, and there we have used KMnO4. So here also we are going to use KMnO4, and also there will be ozonolysis that you have already seen in case of alkenes. So just like similar to alkenes, alkynes can also be oxidized either gently or strongly, and that depends on what type of reaction conditions you are using. Just take KMnO4. You can use it in cold dilute condition, or you can use it with hot concentrated solution, and your products will be different. So that depends on this reaction condition or reaction environment. Now since alkynes are more reactive than alkenes, CC triple bond, there is basically total 2 pi bond and 1 sigma bond. But when you consider CC double bond, there is 1 pi and 1 sigma. So here more loosely held pi electrons are present. So when you are treating it with some oxidizing agent, big oxidizing agent, what it seeks for? It seeks for some negative charge or electron cloud. Now if electron clouds are easily available, so obviously reaction will be better. So that is why alkynes are more reactive than alkenes, because of this higher number of loosely held pi electrons. And as they are more reactive, now you don't have to use conditions that are very harsh. Suppose simply compare these two. For alkene, the condition that you have to apply in case of alkynes, because of their more reactivity, now reaction conditions can be gentler. There will be no problem. Okay. So what is the reason behind it? Why we can use gentle condition compared to CC double bond? The reason is because of its more reactive nature. Okay. So under oxidation, the first reaction we are going to see oxidation with KMnO4. But look at this condition. This is very important. How you are using the KMnO4, that matters. So we are using here cold and dilute. Alkynes are readily oxidized by cold dilute, neutral solution, or alkaline. Now this alkaline is also not very strongly alkaline. It is slight alkaline. What you will get? You will get 1,2-dioic acid. So there will be formation of CO2H group, but that is at 1 and 2 position. So when it is acetylene, you will get dioic acid. But when it is internal alkyne, that is both side you have some R group, obviously now acid formation not possible. Now you will get 1,2-diketone. And if it is terminal alkyne means like this. There will be 2 oxo acid. That means this side there will be formation of acid, but not the other side. So this is internal alkyne RC triple bond Cr, terminal alkyne RC triple bond CH, and acetylene is both side H. So when it is acetylene, you are treating with cold dilute KMnO4, your product will be HOCO COOH. So this is obviously dioic acid, right? Now the second one, if you are using terminal alkyne, now in the right hand that is written here. Understood? Now this reaction is also, and the same applicable for here also, both side it is same. Now here also the same thing that we have already learned in case of alkenes, that when we use KMnO4, KMnO4 is having a very good unique color, which is pink color, and that color will be discharged, because now once it has reacted, it is no longer in the KMnO4 form. It is in some higher less higher oxidation state. In KMnO4 it is +7 oxidation state, but as it has already reacted as oxidizing agent, and here alkyne needs to be acting as reducing agent, so Mn from +7 state, now it is in some reduced oxidized state. So it is no longer in MnO4 ion form, and that is why the color will be discharged. And that is the reason it can be used as a test for unsaturation, and the test is known as Bayer test. So if you are having any hydrocarbon and there is color discharge occurring, so you can say that unsaturation is present. So either CC triple bond present or CC double bond present, but which one is present, that you cannot understand from KMnO4 this Bayer test, because it is applicable for both CC triple bond as well as CC double bond, right? Now the next oxidation, now we are going to use hot concentrated KMnO4. It is not dilute. Now when it is hot concentrated, look at the temperature, 373 to 383, almost 100 degree centigrade, concentrated or strong alkaline solution of KMnO4. Now this CC triple bond, it will be completely cleaved, because now the reaction condition is harsher compared to the previous situation, leading to the formation of carboxylic acids, or it may be CO2 also, depending on what type of alkyne you have taken. So let's start with the simple one, which is HC triple bond CH, where both sides you have some terminal H, and this is the first member. So in this case, what will happen? There will be generation of carbon dioxide. Basically, 2 carbon dioxides will be generated, and there will be also formation of water, which is the fate of these 2 hydrogen. Now, after this, suppose one side we have R group. In this case, the same reaction condition, from the left hand side part, the CC bond is cleaved. So from this part, you will get RCOOH, and from the other part, you will get CO2. So from this side, you are getting CO2, that is the fate. And if I take RC triple bond C, and suppose both sides different R group is present, 2 different types of acids you will be getting, right? 2 different types of acid. So CO2 you will be getting only when you have this triple bond CH. But if there is R group, it is not H. R will be there. So this C triple bond CH part, that is oxidized to CO2. So that you have already seen here. It is oxidized to CO2. So both side here oxidized to CO2. And the triple bond Cr part of alkyne, it is oxidized to CO2H. That is RCO2H. Okay. So this is the difference between hot concentrated KMnO4 or you have taken dilute cold KMnO4. Here the CC triple bond itself is broken, but in the previous case the bond is not broken, it is still there, right? So this is the difference whether you are using mild condition or very harsh condition. So this is the second reaction for oxidation under oxidation category. Now the third one is oxidation with ozone, and this reaction is known as ozonolysis. Though it is not the ozone is not the only reagent. First we treat alkyne with ozone, and in case of alkene also we have seen this reaction. First we treat it with ozone and then we use some reducing agent. So on ozonolysis, alkynes give different products depending on whether the triple bond is external or internal, and that is expected. We have also seen in case of alkyne, depending on what type of R groups are present both sides, we have seen different products, aldehyde or ketone. But this time it will not be aldehyde or ketone, it will be something different. So let's start with the simple one, that is the first member. If you treat it with ozone and also the reducing agent, remember the reducing agent we use mostly zinc and water. It may be some other reducing agent also like dimethyl sulfite. So in this case what we will get, ACO COH. Fine. But if I am using RC triple bond CH, the same reagent you are using, but now what will happen? This side it is RCO and then it is COH. So we are not getting any aldehyde or ketone individually, because in case of alkene what you have seen, the CC double bond itself is cleaved. But here the situation is not like that. Here CC triple bond, it is not that completely cleaved. That is not the case. The CC linkage is still there, but triple bond is gone. Triple bond is no longer present. Still there is one bond, and the fate of this two carbon, now it is 1,2-diketo compound. And this diketo compound, here we have H both sides, but here we have R and H, and that is because of this substitution. So ozone adds to CC triple bond of alkyne to form ozonide, and a detailed mechanism we have seen in case of alkene, the similar type of mechanism. And now we are using the decomposing the ozonide, that is the intermediate. It may be zinc dust water, H2PD. Mostly we do reductive cleavage. It may be Me2S also, and we get 1,2-dicarbonyl compounds. So these are 1,2-dicarbonyl compounds because you have carbonyl group at 1 and 2 position. And remember, if you are not using, suppose you are not using any reducing agent, you are simply using only ozone. Now what will happen? In absence of any reducing agent, the H2O2, which is the byproduct for the first step reaction, that is you are simply treating only with ozone. Remember, in case of alkyne also same type of observation we have seen. Suppose you are not using any external reducing agent, that is you are not using any separate reducing agent, H2O2 is already present in the medium, and that will itself act as the oxidizing agent. So what it will do, it will oxidize the carbonyl compound, and now you will not get 1,2-diketo compound, rather you will get the CC bond cleavage will take place and you will get 2-carboxylic acid. So the same reaction if I write again, but this time I am not writing the reducing agent. Try to understand the difference. So when you are not writing this, so this is the first generated ozonide. You can also write it in this case because same ozonide is formed. But this ozonide, when you treat it with Zn and H2 or any other reducing agent, you get 1,2-diketo compound. But if you are not using any reducing agent, there is already formation of H2O2. But before H2O2 is coming into the picture, first remember water is present in the medium. So there will be formation of HCOCOH. So just like this one as we have seen. But as we know, H2O2 is also there. So you will not be able to isolate the product in this way, because ultimately this aldehyde, basically here you have two aldehyde groups as if connected together. So there will be cleavage at this point. You will get two molecules of HCOOH. So from both sides you will be now getting two individual carboxylic acid. But it is possible only when there is no reducing agent you are using. So be very careful. When a reaction is given, you have to write the product. Just look at the reagent properly, whether any reducing agent mentioned or not. Okay. Now under oxidation, the fourth reaction is combustion reaction. And combustion reaction is reaction with oxygen. Alkynes, just like other hydrocarbons, undergo combustion. Combustion we have seen in case of alkane. We have seen it in case of alkene also. Just like any other hydrocarbon, here also we will get combustion, but product will be different depending on whether it is complete combustion or incomplete combustion. So when it is complete combustion, there will be carbon dioxide, water. But when it is incomplete, you will get CO2 will be there. Suppose some of the alkynes completely combustion reaction, they have undergone complete combustion, but some of them they have not undergone complete combustion. So in that case, there will be generation of CO, C, and H2 is also there, because that is the fate of the hydrogen which is present in the hydrocarbon. So if it is so, then we will write the example here with ethane. So ethane is basically the first member, the simplest one. It burns extremely well, generating extremely hot flame if mixed with pure oxygen. Look at the temperature, very high. Now, because of this extreme, as it burns very well, that is the reason we use, there is a very important application of it, which is the use of oxyacetylene torch. Oxyacetylene, from the name you can understand, acetylene is there, oxygen is there. So these torches that use oxygen and ethylene gas, ethane gas together, and are very effective at melting and cutting metals because it generates very high temperature. Combustion reactions are, exothermic reactions. So it generates very high temperature, and that is the reason these torches are very good for cutting metals. And for cutting metals means you also have to melt it so that the metal is soft and then you can cut it. So very high temperature, for generation of very high temperature, these torches are very good. Now we will see when it is complete combustion, what happens. When there is incomplete combustion, what happens. So I'm treating it with oxygen and we will balance it. Balancing of combustion reaction is very easy. So see what we will do here. Okay, let me write the other two reactions also. But this time it will be CO, not CO2. And another reaction will be, we will write where C is generated. So it is not CO. So the first reaction is complete. The third one and the second one is incomplete. Now if I put, that is if I balance both sides, it is C2H2, right? So from 2 carbon, obviously you should get 2 CO2. And you have total 2 hydrogen. That means H2O, it is already balanced. Now look at the number of oxygen. From these 2 CO2, there is total 4 oxygen. Here total 1 oxygen. That means 4 plus 1, total 5 oxygen atoms. So it should be like this. But if you don't want fraction, what you have to do, you have to multiply 2. Then this 2 is gone. It will be 4. And there will be a 2. So in this way, you can balance this reaction. Now come to the incomplete. And look at the ratio. It is 2:5. The ratio of C2H2 and O2 when it is complete combustion. Come to the second one. In the second one, again from 1 mole of C2H2, there must be 2 moles of CO generation because you have to balance 2 carbon and 2H2, 2 hydrogen atom. That means 1 water molecule. It is fine. But look at the oxygen. 2 oxygen atoms, 1 oxygen atom. So it should be 3/2. But again, if we do not write this fraction, you have to multiply both sides. So now it will be 4 and it will be 2. Okay. Look at the ratio, it is 2:3. So this time, just compare with the previous one, the ratio is decreased. That means for complete combustion, you need 2:5 ratio. But here you are using 2:3. So that is what is incomplete combustion. Come to the third one. Here only one C is written, but it should be 2 and 1. 1 H2. That means 1 oxygen in the right hand side. So it should be half oxygen. But what we will do? We will write it 2. Then it is 2 and it is 4. Now look at both sides. It is balanced. In this case, the ratio is 2:1. Isn't it? 2 moles of C2H2 and 1 mole of H2. So when you have this ratio, you will get the incomplete combustion, which is formation of soot, that is carbon. So incomplete combustion of ethane happens readily if it is allowed to burn freely in air, producing either pure carbon, which is the soot, or that is the last reaction, or it may be carbon monoxide. So this is the third reaction and this is the second reaction. So in this way, 3 different types. The first one complete combustion, the second one, third one incomplete combustion. So combustion related problems, not only here, you will also, these are very important. So that is why how to balance combustion reaction, if you learn it well, it will be helpful for you, not just for organic. In thermodynamics chapter also you will see combustion related problems are there, and you will, most of the time you have to balance those equations. So you should know how to balance properly, and it is very easy, as I have just shown you. Just practice it, it will be clear. Now the fourth type, which is polymerization. So until now, what we have learned? We have learned addition, which we have started in last class. Then we have the reactions, that is because of the acidic character of alkyne. And the third one we have seen oxidation. Now we have reached the fourth one, which is polymerization. There is 2 important types of polymerization that is possible for alkynes. The first one is linear polymerization, and there will be also a cyclic polymerization, that is the second category, where some ring structure will be formed, but this is linear polymerization. Here we will get some open structure, obviously. So what reagent we are using? We are using CuCl NH4Cl. So in presence of this reagent, 2 molecules of acetylene first dimerize. That means 2 acetylenes are there. They will be now connected, and you will get 1 molecule of vinyl acetylene. And if you are treating it with another equivalent of acetylene, that is total 3. In total, there will be divinyl acetylene. So look at this reaction. You have started with acetylene, and suppose there is another acetylene you are taking. In presence of CuCl and NH4Cl, there is formation of CH2 double bond CH, then C triple bond CH. Okay, so this is called vinyl acetylene. So what is happening here? As if this H is replaced by some CC double bond. So this part is called vinyl group, and this part is acetylene. So as if the hydrogen of acetylene, it is replaced by some vinyl unit. Vinyl unit is this one. So this is the connection part, and this is vinyl unit. Okay, so that is why the name is vinyl acetylene. Now another molecule of acetylene if we take, then what will happen? Here this H also as if replaced by some another vinyl group, right? So this side it is replaced by one vinyl group, and another side it is replaced by some another vinyl group. Okay, so it will be Cu2Cl2. So either you write CuCl or Cu2Cl2, same thing. So divinyl acetylene, look at the name. The first one is vinyl acetylene, this is divinyl acetylene because of 2 vinyl group. Vinyl acetylene is widely used. That is the first generated compound is widely used in the manufacture of chloroprene. Now what is chloroprene? We will see the structure. Now this chloroprene, it is actually the monomer of a polymer, and the polymer is neoprene, which is having the monomer, and that monomer is actually generated from this vinyl acetylene. That is why it is important. Okay. So here two molecules of acetylene we have taken in presence of CO2, Cl2 and H4Cl. First there is, this is CC double bond. First there is generation of vinyl acetylene, that is just this reaction. And then in presence of HCl there will be formation of, that is the source of chlorine is from this Cl. So what is happening here? See, this type of alene structure is generated. This is called alene, where a common carbon is there, where both sides there is double bond. So vinyl acetylene when combines with hydrochloric acid it forms 4-chloro-1,2-butadiene. This is 4-chloro-1,3-butadiene. So let me put the numbers. Parent chain total 4 carbon, 3 and 4. So at one position and two position you have 2 in, and that is why the name is ending with diene. Their positions are 1, 2. Parent chain is but, 4 carbon, and at 4th position there is chloro. So that is why the name is 4-chloro-1,2-butadiene. And this is also a alene type of derivative. But it will not be at this position. Ultimately there will be rearrangement. So what is happening here? As if this CCl bond is broken, and it is this double bond is also shifted to the terminal position, and now it is at this carbon. The chlorine is there. So why we are calling it rearrangement? Because number of atoms we are not changing. Only the position of these atoms are changing. So that is why it is rearrangement. So it is rearranging to form 2-chloro-buta-1,3-diene. So now it will be having the name chloroprene. That is the common name we use, but actual IUPAC name if you want to write, it will be 2-chloro-buta-1,3-diene or 1,3-butadiene. Both are fine. So at one position you have double bond, at 3 position you have double bond. So that is why it is 1,3-butadiene, but it has substituent at 2 position. So 2-chloro-1,3-butadiene we are getting starting from 4-chloro-1,2-butadiene. So this is the rearrangement occurring here, and this chloroprene is the important compound we are getting ultimately from this reaction, and this chloroprene is actually used as monomer for the formation of neoprene, which is its polymer. Okay, so this is linear polymerization. Now for this linear polymerization, we'll see discuss some more information we have to see here. For the synthesis of polyacetylene or polyethane, where the repeating unit, look at this, this is the repeating unit. A variety of methods can be used. And in this case, for example, one catalyst is, you can see the name Ziegler-Natta catalyst. Ziegler-Natta catalyst is, it is not YPR, it is whole 4. So with titanium, O isopropyl group is attached. IPR means isopropyl group. Isopropyl group is CH2-methyl. And when there is oxygen attached, it will be OIPR. So if this type of groups are attached 4 times with titanium, that is TiOIPR. Basically, I should be written like this, right? IPR whole 4 in presence of triethyl aluminium. That is the Ziegler-Natta catalyst. So a variety of methods are there. It is just one catalyst example you are seeing have been developed from gaseous acetate. So different types of polymerization is possible, and that depends on what kind of reaction condition we are using. Also the temperature is very important point here. So this method allows control over the structure and properties of the final polymer, and that is dependent on the what temperature you are using, what type of catalyst loading you are using. Sometimes also there is variety of catalyst. Catalyst loading means what is the amount that is compared to your substrate. How much catalyst, we know catalyst we use in very minute amount compared to suppose 2%, 3% or 10%, for example, MC. So how much you are loading, depending on that, we can have different types of products. Though it will be, as you can see here, suppose you are starting from acetylene and this is the catalyst. So see, slight difference you can understand. It is not O isopropyl group. It is simply N-butyl group. So with titanium, as if oxygen attached and then linear 4-carbon chain. So if 4-carbon chain, if 2 more chains are attached, so that is TiON-Bu whole 4, triethyl aluminium. And it can be also group like this. So in general, it is basically TiO R group, as if total 4. Now this R group may be a linear chain, it may be isopropyl, but whatever it is, the catalyst nature is like that. Now look at the temperature. If it is -78, you are getting this type of structure. Try to understand what is the difference. Here it is zigzag type of shape, but here the shape is different, isn't it? So as if both the hydrogens on the same side, cis type of structure, and both the larger groups are on the same side. But here that is not the case. It is zigzag because the hydrogen, it is completely as if the trans arrangement. So when it is 150 degrees centigrade, you are getting this type of structure. When it is -78, you are getting another type of polymer. And from, suppose this is type A, this is type B. From A to B also you can convert if you are increasing the temperature. So it is thermal isomerization because it is isomerization. Total number of atoms, carbon, hydrogen, same. You are simply increasing the temperature, and from this type of C structure, it is converted to trans structure, right? Now, if you are doing further heating, there will be cross-linked brown polymer, and it is not conjugated double bond. So all these are conjugated double bond, isn't it? But when you are heating it further, there will be cross-linking. Suppose from this side there will be another chain, from this side there will be another chain. So this is cross-link. And when we are increasing temperature further, then thermal decomposition will occur and it will be converted to some other. Details not required, but what I'm trying to make you understand is that just by varying the temperature or catalyst loading, we can have so many variety. So at least try to remember this. When it is low temperature, we are getting this type of structure where it is as if the larger groups on the same side, Z type of structure or cis type of structure. But when it is high temperature, it is trans arrangement. And A to B conversion, that is also possible, which is thermal isomerization. So we'll stop here, and there is also cyclic polymerization possible that we'll discuss in the next class. Thank you for listening. We are ending the session here.